Hi Year 11, Mr. Vinod here again. In this video we're going to walk through the different types of acid-base, otherwise known as neutralization reactions. So an acid and a base reaction is going to involve one of the common acids that we know, which could be hydrochloric acid, sulfuric acid or nitric acid. But what about the types of base? There are actually several different types of base. Metal oxides, so a metal being a metal positive ion with an oxide ion. So an example of that is calcium oxide. We've got our calcium cation and our oxide anion. Another type of base is a metal hydroxide. An example of that might be sodium hydroxide. Again, there's our metal, there's our hydroxide. Another type of base is a metal carbonate. So again, we're going to have a metal, this time potassium, and carbonate is CO3. That has a 2- charge when it's in its ionic form. The fourth is metal hydrogen carbonates. They're very similar to carbonates, and an example of that is sodium hydrogen carbonate. Again, the metal is sodium hydrogen carbonate. There's that CO3 carbonate, hydrogen with the H. So those are the 4 types of bases that we're going to look at in this video. So this is the general equation for an acid-base reaction. An acid will react with a base to produce a salt and water. When I say salt, I don't necessarily mean the salt you put on your eggs. There are many different types of salt. That particular salt is called sodium chloride, the one we season our food with. And there are some other ones that we season our food with too. But there are many different types of salt. Some salts are highly toxic and we would not want to be eating them at all. So in our neutralization reaction that we're going to look at, an acid always has H plus in it. So hydrochloric acid, sulfuric acid, nitric acid, they all start with H because they have H plus in them. And the rest of the acid is a non-metal or a non-metal group. I'm symbolizing that by NM. And that group will be an anion that has a negative charge. So for example, chloride, Cl minus, is part of hydrochloric acid, or sulfate, SO4 2- is part of sulfuric acid. The 2 bases that we're going to look at with this equation are metal oxides and metal hydroxides. So we could look at sodium oxide, sodium hydroxide. There'd be 2 examples we could look at here. We're going to form salts as part of this reaction. Now a salt is an ionic compound. And it's an ionic compound where the metal comes from the base and the non-metal comes from the acid. So part of the acid, the non-metal part, goes into the salt. Part of the base, the metal part, also goes into salt. And when you have those 2 parts together, they form that ionic compound. That is the salt. If we look at the rest of what we have here, we've got H pluses and oxide or hydroxide. Those parts don't go into the salt. They go into the other product of this reaction, which is water, H2O. So our H plus will go into water, and our metal oxide or hydroxide will also go into the water. Let's take a look at some specific examples. Here I have nitric acid and sodium hydroxide, and we need to determine what their products are going to be. Now our general equation, as we saw before, was acid plus base makes salt plus water. So we have our acid sorted, it's nitric acid. We have our base sorted, it's sodium hydroxide. It meets the criteria of a base because it's a metal, which is sodium, hydroxide, metal hydroxide type of base. So we need to determine what the name of our salt is that we're going to form, and we already know what that 4th product is going to be. It's water. So I can go ahead and write water straight into my equation there. So this is a word equation. So when determining the name of our salt, there's a little trick you can use. The first part of the name of the salt is from the metal and the base, sodium. The second part of the name comes from the non-metal group in our acid. In this case, there's the NO3, which gives nitric acid the name nitric. So we can remember that nitric becomes nitrate. If we had sulfuric, it becomes sulfate. If we have hydrochloric, it becomes chloride. So those are the three acids that we're going to be using quite a bit, and this is how their name changes as it becomes a salt. So let's go ahead and write the balanced chemical symbol equation for this reaction, where nitric acid reacting with sodium hydroxide forms sodium nitrate and water. So the formula for nitric acid is one you need to have memorized, HNO3. Sodium hydroxide is a compound that's made of Na plus and OH minus. So it has the formula NaOH. They're going to react together to make sodium nitrate plus water. Water, there is a formula you need to memorize, H2O. For sodium nitrate is made up of Na plus and NO3 minus. There's the sodium, there's the nitrate. Because there is 1 plus and 1 minus, this ionic compound is balanced and electrically neutral by having just one of each ion present. When we write its formula, we leave the positive and the minus out. So we would write it as NaNO3. That's one example of an acid-base reaction writing its word and balanced symbol equations. Let's look at another example, sulfuric acid and potassium oxide. Again, we have an acid and we have a base. This particular base is a metal, potassium oxide, metal oxide. So again, we're going to form a salt and we're going to form water. Which salt we're going to form, we can determine from the particular acid and base we're using, but water is always going to be a product. So we can write water over there. Now again, when naming our salt, the first part of the name comes from the metal in the base, potassium. The last part of the name comes from that non-metal group in our acid. Sulfuric becomes sulfate. So there's our word equation. Now we need to turn that into a balanced chemical symbol equation. Sulfuric acid has a formula you need to memorize, that is H2SO4. Potassium oxide is a compound made of ions, so we need to figure out its formula. It has potassium, K+, it has oxide, 2- in it. Because we have 1 plus and 2 negatives, this ionic compound would not be balanced if we just wrote KO. I have 2 negatives, only 1 positive, so I need another positive to make this ionic compound electrically neutral or balanced. Now I have 2 pluses and 2 minuses, and the formula for that would be written as K2O. So there's my sulfuric acid, there's my potassium oxide. I now need to write the formula for potassium sulfate. Again, let's go through the same steps. Potassium is K+, sulfate is SO4, 2- from our ion table. I've got 2 minuses and only 1 plus, so again I need another plus, and they will all add together to give me an electrically neutral compound of K2SO4. And again, the formula for water is plus H2O. I'm just going to write my equation down the bottom there. And there we have our nice balanced chemical equation just there. H2SO4 plus K2O forming K2SO4 plus H2O. Let's just check that it is balanced. I said it was balanced, but is it? Well, I've got 2 H's there. I've got 2 H's there. So the H's are balanced. One little trick I use is put a little tick under each element to check it is balanced. I've got 1 sulfur there. I've got 1 sulfur there, so they're balanced. I've got 4 oxygens there plus 1 there is 5. I've got 4 oxygens there, plus 1 there is 5. So oxygens are all balanced. And I've got 2 potassiums there and 2 potassiums there, so potassiums are balanced as well. So yes, that is a balanced symbol equation for the reaction between sulfuric acid and potassium oxide. Now let's take a look at the next type of acid-base reaction. We're still going to be using the same acids, but this time our base is going to be those metal carbonates, and this also applies to metal hydrogen carbonates. The products are ever so slightly different in that we don't just make a salt and water, but now we also have carbon dioxide being produced, otherwise known as CO2. That's its formula, molecular formula. So let's have a look at how we form the salt again and what parts form the water and the CO2. Well, just like before, the non-metal anion from the acid and the metal cation from the base, those two parts still join together to make our salt. The salt being the ionic compound where the metal cation came from the base and the non-metal anion came from the acid. And again we have the H plus from the acid, and this time we have CO3 2-. That's the carbonate part in our base. So those two parts are going to join together to make the rest of our products. So the H plus and part of the carbonate, one of the O's, will join together to make our water. And then the C and a couple of the O's will be left to form our CO2. So a handy way that I remember this reaction is carbonates make carbon dioxide. That's a handy way to remember that extra product that is produced. Now, because carbon dioxide is produced, one thing we should see if we were to observe this reaction, we should see bubbles. We would not observe that for a metal hydroxide or a metal oxide. The bubbles would not be produced as carbon dioxide is not produced. So that's a test we can do to distinguish between different types of bases. Let's have a look at that reaction now. So here I've got some hydrochloric acid in a beaker, and to that hydrochloric acid I'm going to add some sodium bicarbonate. Sodium bicarbonate behaves in the same way as sodium carbonate. Hydrogen carbonates and carbonates behave in a similar way. So as I add some of that bicarbonate to our hydrochloric acid, you should hear and see something. So you can see there's some fairly excessive bubbling. That's the carbon dioxide being produced and coming up out of that reaction, out of that solution, into the atmosphere. So now let's again look at some examples of these types of reactions and see if we can write their word and symbol equations. The first one we'll look at is hydrochloric acid and calcium carbonate. So we straight away know two of the products that are going to form. We're going to have a salt, and we need to figure out what that salt is going to be, but we're always going to have water, and we're always going to have carbon dioxide produced by an acid carbonate reaction. So those two products we know, but we need to figure out again what that salt is going to be. So again, I take the metal from the base, and that forms the first part of the name, calcium, and I take the non-metal from the acid, which is that hydrochloric bit. Hydrochloric makes chloride. So calcium chloride is going to be our salt, and we're going to have water and carbon dioxide also produced. Let's now write the symbol equation. Hydrochloric acid is HCl. Calcium carbonate, I'm not going to go through the same extensive process of balancing the ionic compound. To learn more about how to do that, you can refer to the previous videos. Calcium carbonate is CaCO3. Calcium chloride, the ionic compound, has CaCl2 plus water and CO2. Let's go through and balance this chemical equation. So, I have one hydrogen on the left, but I have two on the right. To make them the same, I put a big 2 in front of the HCl. Now I have two H's on the left. That big 2 also means I have two chlorines on the left, and I have two chlorines on the right. So my chlorines and my hydrogens are balanced. I have one calcium on the left, one calcium on the right. They're balanced. 1 carbon on the left, 1 carbon on the right, balanced. 3 oxygens on the left, 1 there and 2 there on the right, so oxygens are also balanced. Let's look at another chemical reaction. Nitric acid and sodium carbonate. So again, when determining the products, I take for the salt the metal from the base, sodium, and that non-metal group from the acid, nitric, makes nitrate. What are the other two products that always form in an acid-carbonate reaction? Hopefully you said water and carbon dioxide. Again, that carbon dioxide is specifically produced from carbonates and hydrogen carbonates when they react with an acid. Let's write the symbol equation. Nitric acid is HNO3 from memory. Sodium carbonate, balance the ionic compound. Na is a positive ion, carbonate is a 2- ion, so we need 2 sodiums to balance that. Sodium nitrate, Na is a +1, NO3 is a -1, so just one of each of those needed, plus water, plus CO2. Let's go through and balance this one again. 1 hydrogen on the left, 2 hydrogens on the right. Again, I'm going to need to put a big 2 in front of the acid. 2 nitrogens on the left, 1 nitrogen on the right. I'm going to need to put a big 2 in front of my sodium nitrate. Now I have 2 N's on each side and 2 H's on each side as well from before. Let's look at our oxygens. I've got 3 O's there and 3 O's there, so 6 total on the left. But hang on a second, this one's multiplied by 2. So I've got 2 times 3 is 6 O's there, and 3 O's there makes 9. So 9 O's on the left. Well, I've got 2 times 3 is 6 there, plus 1 is 7, plus 2 is 9. So I've got 9 on both sides, and we're good to go. Coming over here, I've got 2 sodiums, 2 sodiums. Sodiums are good. 1 carbon, 1 carbon, carbons are good. So that's a balanced symbol equation and a word equation for that reaction. Let's look at another reaction. Sulfuric acid and sodium hydrogen carbonate. Hydrogen carbonates react in the same way as carbonates. The same products are formed. There's just an extra H in the base. So let's work out our salt. Again, we take the metal from the base, sodium. We take the non-metal group from the acid, sulfuric becomes sulfate. The other two products for an acid and a type of carbonate reacting is going to be water and carbon dioxide. Let's see if we can write the symbol equation. Why don't you pause here and have a go? Sulfuric acid is H2SO4. Sodium hydrogen carbonate, the sodium ion is Na+. Hydrogen carbonate is HCO3-, so +1 and -1. Just need one of each. Sodium sulfate, Na is +1, SO4 is 2-. So I need 2 Na pluses to balance my SO4 2-, plus water, plus CO2, carbon dioxide. Let's go through and balance this one. So this is a slightly more difficult one to balance in that we've got hydrogens in multiple places and oxygens in multiple places. So let's look for something that's not hydrogen or oxygen and balance them first. The key difference I can see straight away is that I've got 2 sodiums here and only 1 sodium here. So let's balance those first. 2 there, 1 there. Let's put a big 2 in front. Now my sodiums are good. Another little trick you can use, when we have an acid-base reaction, the non-metal group from the acid stays together. So that SO4 stays as a SO4 and forms there. So we can actually kind of think that SO4, you can treat it like one whole particle when balancing the equation and say that the SO4s are good. So let's look at the rest now. I've got 2 H's there, and I've got 2 H's there, which gives me 4. I've only got 2 H's on the right, so I need to have 4 H's on the right. So H's are good. I've got 1 carbon on the left, 1 carbon on the right, but hang on a second. 2 carbons means I need 2 carbons. Now the carbons are good. I almost fooled myself there. And lastly, oxygens. I'm going to ignore the ones that are part of SO4 because they've stayed in SO4. So I'm just going to focus on the ones here. 2 times 3 is 6 O's there, and I've got 2 there, and 2 times 2 is 4 there. 2 plus 4 is 6. So my oxygens are good as well. So there we are. I hope you found that helpful. That's how to predict the products of an acid-base reaction, whether it's a oxide, hydroxide, carbonate, or hydrogen carbonate. Hope you found this helpful.